Okay, moving on to the next part of our discussion on optics. Let's have examples part 1. So let's start with sample problem number 1. Consider the following situation. In a physics lab, light with wavelength 490 nanometers and travels in air from a laser to a photocell in 17 nanoseconds. When a slab of glass 0.840 meters thick is placed in the light beam, with the beam incident along the normal to the parallel faces of the slab, it takes the light 21.2 nanoseconds. So it takes the light slightly longer to travel from the laser to the photocell. What is the wavelength of light in the glass, in the slab of glass that was placed between the laser and the photocell? So, we have the wavelength of light in air, 490 nanometers, or 490 times 10 to the negative 9 meters. And the time of travel of light in air in this initial situation is 17 nanoseconds. So let this be initial time Ti, 17 nanoseconds, or 17 times 10 to the negative 9 seconds. The thickness of this slab of glass, let that be the glass, 0.84 meters. The problem tells us that the final case, the time it takes the beam of light to travel from the laser to the photocell is 21.2 nanoseconds. So let this be our final time TF. TF is equal to 21.2 nanoseconds or 21.2 times 10 to the negative 9 seconds. We are looking for the wavelength of light in the slab of glass. So you have lambda glass. Initially, the light simply travels in air, traveling a distance that will take it 17.0 nanoseconds. So the distance between the laser and the photocell is such that it will take time to travel 17.0 nanoseconds. Which means, knowing that the medium is air, speed of light in air is basically the same as the speed of light in vacuum. Knowing that light is traveling in air, we know the speed of light to be c. C is constant. Speed of light is constant. Thus, we are able to calculate the distance traveled of the light beam. D air initial is equal to Ct initial. We know C, we know T. Thus, we are able to calculate D air initial to be 5.1 meters. Now, D air initial is the initial case. Light traveling in air travels from a laser rather. So light travels from a laser to a photocell. This means the distance between the laser and the photocell is the air initial, 5.1 meters. In the final case, we place a slab of glass 0.84 meters thick between the laser and the photocell. Thus, the final distance traveled by the laser in the final case is comprised of two parts. Distance traveled by the light in air plus the distance traveled of the light in the glass slab. Note that the positioning of the laser and the photocells are not changed, which means D final is just equal to the initial distance between the laser and the photocell. So D final is just equal to D air initial. Isolating D air final, since we know D glass, D air final is equal to D air initial minus D glass. Knowing D air initial, knowing D glass, we are able to calculate D air final 4.26 meters. Since for D air final rather, light is traveling in air, so the speed of light in air is still c, we are able to determine the time of travel of light in air in the final case. Once again, speed of light is constant, so uniform motion gives us time of travel is equal to distance travel divided by speed. So T final air is equal to D air final divided by C. Thus, we are able to calculate the time of travel of the light beam in the final case, time of travel of the light beam in air in the final case, 1.42 times 10 to the negative 8 seconds. Knowing that it takes the light beam for the final case, it takes the light beam to travel from the laser to the photocell, it takes the light beam 21.2 nanoseconds. And in air, it takes the light beam 1.42 times 10 to the 8 power seconds. The final time of travel is just equal to the time of travel of the light beam in air for the final case plus time of travel of the light beam in the glass slab. Knowing TF and we know T final air, we are now able to calculate the time of travel of the light beam in the glass. 7 times 10 to the negative 9 seconds. And knowing T final glass, the time it takes the light to travel through the slab of glass, knowing T final glass, knowing the thickness of the glass, we are now able to determine the speed of light in the slab of glass. Again, speed of light is constant. You have uniform motion, which gives us the speed of light in the glass. V glass is equal to thickness of the glass, D glass, divided by the time it takes light to travel through the glass. T final glass. We know the thickness of the glass. We know the time of travel of light in the slab of glass. Thus, V glass is equal to 1.2 times 10 to the 8 meters per second. And knowing the speed of light in a particular medium, we are able to determine the index of refraction of that medium. N glass is equal to C glass over V glass. Another equation for index of refraction is lambda air divided by lambda glass. Now, lambda air, note that this should be lambda in vacuum, but since we are taking the index of refraction of air to be the same as index of refraction of vacuum, wavelength of light in air is pretty much the wavelength of light in vacuum. So we can use the wavelength of light in air for this equation. Taking C over V glass is equal to lambda air divided by lambda glass. Isolating lambda glass, we have lambda air, V glass divided by C. We know lambda air, we know V glass, and we also know the speed of light in vacuum, we are able to calculate the wavelength of light in this slab of glass. 1.960 times 10 to the negative 7 meters, or 196.000 nanometers. Next, we have sample problem number 2. A parallel beam of light is incident on a prism as shown in the figure. You have a prism of angle A on this corner. You have two beams of light, parallel beams of light, incident on the prism. One is incident on this side of the prism, and the other beam of light is incident on this side of the prism. Part of the light is reflected from one face and part from another face. The two reflected beams of light, the angle between these two beams of light is angle theta. Show that the angle theta is twice the angle A. So show that theta is twice of angle A. So theta is equal to 2A. So show that theta is equal to 2A. Now, the two beams of light reflect off the sides of the prism. So you have law of reflection. The two beams of light are such, according to the figure, the two beams of light are incident on the prism such that you have, if we divide angle A into 2, we have angle of this beam of light with respect to the prism, with respect to this side of the prism, you have A over 2, and on the other side, you have A over 2. Angle of reflection tells us the incident angle and the angle of reflection are the same. So you have angle B, you have also angle B on this side. And the same on the other beam of light. Since the two beams are parallel, meaning the reflection of the two beams will also be identical. The beam of this beam of light reflects off this side of the prism. You have angle of incidence, angle of reflection. If this is B, this is also B. So angle of incidence, angle of reflection, law of reflection tells us that they are the same. Geometry tells us that if this is A over 2, angle B, the remaining angle will be A over 2. So A over 2, on the other side, you also have A over 2, which means angle theta is equal to A over 2 plus A over 2, which tells us that theta is just equal to 2A. Show that the angle theta is twice the angle A, and that's what we have done. Theta is equal to 2A. Moving on to the next example, we have sample problem number 3. When a rectangular metal tank, as shown in the figure, rectangular metal tank, depth of 0.6 meters and length of 1 meter. When this rectangular metal tank is filled to the top with an unknown liquid, an observer with eye level at the top of the tank can just see the opposite bottom corner F of the tank. So for this situation, an observer with his eyes on the level of the top of the tank, he can just see the bottom corner F. Determine the index of refraction of this unknown liquid. So let the depth of the tank be small d. D is equal to 0.6 meters. Let the length of the tank be length L. L is equal to 1 meter. Now, for the observer to be able to see point F, light from point F must reach to the other corner, to the opposite corner of the tank, move from liquid to the other medium, liquid of medium N to this medium, air, medium N2, air. So light will transfer from one medium to the other. You have refraction of light, and that light will reach the eye of the observer. So you have angle of incidence theta 1, and with respect to the normal line, you have angle of refraction theta 2. And we see that theta 2 is just equal to 90 degrees. N1 is the liquid. We are looking for N1, index of refraction of the unknown liquid. N2 is air. We know the index of refraction of air to be just equal to 1. Using the geometry of the situation, theta 1, we can use tangent of theta 1 equal to opposite over adjacent. L divided by D. Getting the inverse tangent, we are able to calculate theta 1, 59.03624,347 degrees. We have angle of incidence theta 1, angle of refraction theta 2, we have index of refraction N2. Looking at the law of refraction or Snell's law, N1 sine theta 1 is equal to N2 sine theta 2. The only unknown is N1, index of refraction of the unknown liquid, what we are looking for. Isolating N1, N1 is just equal to N2 sine theta 2 divided by sine theta 1. Plotting in the values, we are able to get the answer. We are able to get the index of refraction of the unknown liquid, 1.166. And that's it for now. That's it for our discussion on examples part 1. We'll continue our discussion of examples in the next video. We'll have examples part 2, wherein we look at a few more examples. So again, that's it for now, and thank you for watching.